Many thanks for the invitation. And this is this talk is concerned to Stan method in the sense of the following. So this is what we treat is the case where probability itself or distribution itself has uncertain, which was firstly proposed by economist Frank Knight. Is the father of the Frank Knight we know, okay, who is not a probabilist, who is an economist. Sorry? Yeah, same name, Frank Knight. Okay. So we at year 1913 proposed by Louis, we have a program, a 6-week program here discussing this probability. 2000 here, yeah. 13, I think, no? It's 13, I think. So, in that time, I didn't know about I didn't know about this Stan method, but Louis gave a very excellent talk. I began to think about this. This is the beginning of my interest to, because in that time we already have the so-called central limit theory and law of large number. But it's heavily depends on PD. In fact, it's we tried long time. It doesn't work because it's nonlinear. Nonlinearity is very important, so we just cannot use the classical characteristic function method. But we so I take long time to suddenly find that for analysts, in particular for Krylov has a very deep result in PD, in fully nonlinear PD. In fact, a kind of PDE for Hamilton-Jacobi equation, second order Hamilton-Jacobi equation, which can be used to solve this this problem of the limit. Okay, the limit existence and uniqueness of the limit. Then since we see there is another method in Stan method, we try to if it worked here, and this was collaborated with Qiman Shao, with Fang Xiao, who is very well known, with Fang Xiao, and also with Song, who is in academic science, and also with my former student Hu. So we, but it's not that easy. I will explain. It's not, we cannot directly move to we try many times. Finally, we understand something. That's, we can use this method to improve the convergence rate for this nonlinear, what we call nonlinear central limit theory, and the nonlinear law of large number. So the problem is that we, as I mentioned, there are serious problems in economics and finance for the so-called IID. Okay, the so-called IID is in economics is according to Frank Knight, there's no sense to work with this. And also, very recently, we know the larger data. Many people talk about the large data. They say that the main difference from the actual probability statistic and the real world data is that there are no IID. Okay. So what we can treat in this case for this is so this become the main idea is that we have of course we have this kind of uncertainty of probability, but we have no way to cancel this. Okay. In this case, there is one way called robust economies. They treat such like this. I don't know, but I take the worst one. Okay, the worst one because for example X is a loss, so I can take expectation of loss, the so-called expected loss, but I don't know to use which one. We can use this one, but in this case, this EX it becomes nonlinear. Okay, in the left hand, this operator like expectation, which is a sublinear expectation. So sublinear expectation is one of most, in my opinion, is one of the most important nonlinear expectation. Sometimes we can take max min, min max. We can take other many things, but this one is, I think, the fundamental one. Once we can understand this, we can understand many things for nonlinear expectation. So so the idea is that we just use this and we think anything like under this sublinear expectation, such like I think IID is under this sublinear expectation. I treat law of large number. The law of large number is in this framework. Is in this framework. We have this so we know that the linear expectation can have one correspondent to a probability. Okay, this is a so-called Daniel-Stone theory. It's given us to this, but we can treat like we first already have a sublinear or nonlinear, even nonlinear expectation defined in this space in which omega is the same like what we treat, but we directly treat the H as the random functions. Random functions is a functions of omega defined in omega, which in this case the sublinear expectation we have is just have monotonicity, constant preserving, sublinear, and in many cases, we need the downward continuity. Just with this, we have the so-called nonlinear version of Daniel Stone theory, telling us that in this case there exists a subset of probability defined on omega and sigma algebra of H, such that in fact we have this kind of the so-called representation. Okay, this representation. So in this case, I know how to treat this is equivalent that I know my probability uncertainty, the subset of probability uncertainty, in which we can treat like this. Okay. There are two important. One is the so-called identically distributed. We see that x and y are identically distributed if for any test function phi, this two is the same. It's exactly telling us that the distribution uncertainty are the same. X and y have the same uncertainty. So if for example this is bigger than this, means that the uncertainty of x is larger than the uncertainty of y. If this is, and the independence becomes one way. Okay, one way independence. Independence means that y is said to be independent of x if I calculate this. I can calculate this expected value in the sense that first I can put x equal a constant and then calculate this one, and then again I put x to the random variable and calculate to this. So this is really one way independence. The other y is independent of x, but the x can be very heavily dependent on another. That's why we can treat many situations which is interesting. Okay, we can treat the case where in fact we can prove that if x is independent of, also independent of y, in this case it's become linear. Everything becomes linear. So it's just in this way. And just this is the whole notations. Okay, the whole notation is already given, and then we can we can think about the ID. The so-called ID is because we have identity distribution. We have like this. If we have a random variable, a sequence random variable, and we have the first one, and then we have xi plus 1 is independent of xi to xi, x1 to xi for all I, then we see that this is ID. So this is one-way ID. It's just one-way ID, but in fact, for any phi, this is still ID. Okay, this is just like a classical situation. It's for any phi, this is still ID, and then we can example. One example is very simple, that we have both black and white. Okay, we have 100, the totally 100 balls, which is white and black, and then we put them inside a black box. We don't know which one is which one. We even don't know how many numbers. Okay. We for example, we only know the number of black is between 40 to 60. Or other cases the same. We even know this, and if what the game is, if I get a white one, I get $1, and otherwise I lose $1. Okay. In this case, I have this random variable, and this random variable is I cannot say in classical situation it's IID, because it's I don't know the number, and each time I do this, I repeat this game, and each time the number can change. Okay, if otherwise you can, for example, you can use statistics. The statistic cannot work because each time it's changed. It's like our life. Okay, each time everything changes. But this kind of thing constitute IID. Now this is the IID. So this is the first, and in general, so this is IID, and this IID is kind of what we call nonlinear Bernoulli. Okay, if you just fix this, I know 40 black balls, then it's become Bernoulli, and this is the nonlinear, what we call nonlinear Bernoulli, which is the IID, but and in general, the general situation is I don't know this. Okay, I have a machine which can produce. So
just a quick question. In this case, I can see that x2 is dependent on x1, but we said that x1 should not be dependent on x2, otherwise it becomes trivial.
Yeah. If x and y are mutually independent, it becomes trivial.
In this case, explain the intuition why x1 is not independent of x2. Is that the case? You said x2 is x1.
This is the case.
X1
Yeah. Exactly. So because my advisor, he know everything of the balls output in history, and he can do things like what so at worst situation is like this. So my advisor, they can change the number according the information he get. He get the information of the first, the second to the s time. Okay, he knows this situation, so it's not independence. It's like this, the independence. And then you can so here in general case, I have a machine. This machine can produce random numbers, but among these distributions, okay, among these distributions, they can produce among this, but you don't know which one, which f theta they cite. Okay, you don't know this, and then you just but you don't know this, but what you choose is completely independent. It's completely random. Okay, random. That means I don't know which f theta but they produce completely randomly. In this case, we can have the more general, the general situation of IID. Okay, this is the general, and this general situation of IID is very, very large. It can be very small. It can be very large. It depends. It depends what it can. For example, it can be. For example, I have mu, lower mu and upper mu. I have lower mu. I have a random variable which can happen in any case between this two number. Okay, so you the f theta can be the whole distributions in between or in this. I have a whole distribution. So in this case, this f theta is very easy to be calculated. The whole, which is in this case, of course, if I take any phi of x dx super theta, which is in fact, which is very complicated, but which is in fact phi y in mu. Okay, this is very, in some sense, extreme case become very easy. Extreme case become very easy. You just know it's. I don't know which one, but I know this kind of phi y. Okay, I know this. I know this how to calculate this. This is called, this kind of called the maximal distribution. Is a maximal distribution. We write it like this. Okay, this is one of the things we cannot find a correspondence from the classical situation. Or it's if you like, is constant. Okay? The corresponding constant. I have uncertainty of constant. It becomes to this one. Of course, is but this kind of if I have this kind of ID, x1, x2, x3. Each one is independent from the precedent one, and each one is mu. So I have such kind of random variable sequence. Its uncertainty is all statistical, all random sequence, all possible random sequence which is bounded between upper mu and the lower mu. So you know this IID can be very, very large, can be very large. This kind of IID can be used to treat many things. Of course, what remains is how we can narrow this lambda, this mu. How we can narrow this mu. If I really can manage through after my data to narrow this to be one number, then I know it's constant. It's just a classical situation. Okay, it's just classical. But otherwise, I know that if it's relatively small, I can also satisfy to say that I have a maximal distribution, which is between a very narrow number. Okay. On the other hand, in some sense, in some times I cannot treat. I cannot narrow this lower mu and upper mu. In this case, I just say that I have two important uncertainty. Okay. So this is what. Do you have some question? Okay. So it happens that for this kind of thing, we have law of large number and the central limit theory. This is a very interesting phenomenon. And I just quickly come to here is okay. This is the law of large number. The law of large number telling us that if I have this kind of ID, which is what like I say, it can be any data. Okay, can be any random data. If I can have this, then I put them together. This is exactly like the classical situation, but for any given phi, then when n tends to infinite, it is the maximal distributed. It is just the maximal distributed. And then the upper mu is just the sublinear expectation of y1, and the lower mu is is this one, okay, minus e minus y1, minus e. Okay, so this is why this is of course we have another one is this is the law of large number. Sorry, this is the central limit theory. We can prove that in this case, this is exactly like what we treat, like the classical situation. And we see that X is n is normally, nonlinear normally distributed with two parameters. Because we assume the upper mu is equal to lower mu, so it's becomes zero. So here we have this. But it's not, this is just a notation. It's not to say that the uncertainty is just the classical Gaussian with mu sigma square in between. In fact, what we say that X is like Gaussian if X plus X bar A B is the same distribution like square root of A square plus B square times X. Okay, where X bar is independent of and identically distributed like X. So this is what we call. And this is equivalent. This is equivalent. But of course, in classical situation, you have Gaussian. You have centered Gaussian in this case. But this is for this case, it's equivalent to say that if I define UTX equals U phi x plus square root of Tx, then dTu equals to G dxxu. Okay, with U 0 x equal to phi x, where G is what? G A is 1 over 2 sigma upper bar, sigma upper bar, the positive part of A plus sigma lower bar, the negative part of A, which is like this. I have such kind of nonlinearity, okay, which is G, okay, my G. This is A. You see, we have this kind of, so what we define, if it satisfies this, we define like this, X like this. And then I suddenly, if I should prove this, I suddenly meet a very important nonlinear expectation, the PDE, okay, nonlinear PDE. Very important nonlinear, which is not really smooth, because in this there is angle. I tried to find many times, and then finally find that Krylov, he has a result to telling us that this equation has 2 plus alpha differentiable equations. So this is quite important. Of course, we use this result, and but this you know the story of Krylov is that Krylov spent almost 20 years to convince people that his result is correct. Okay, because he used some method that the classical like people like Nuremberg, like they don't use. Okay, he didn't know, so he used a very long time to convince people about this. But what we want is from Stan equation is that we use probability method instead of PDE to prove this problem. Okay, to prove this problem. This is our purpose. How we can use the Stan method to prove this, and also prove the law of large number. Because even for law of large number, we still use the method of Krylov. We just like a perturbation, we put a small epsilon, then let epsilon tends to 0. We in this case we always can profit this PDE. So question is, how can we don't do this by this Stan method? So firstly, how about the Stan formula? The corresponding Stan formula is what? This also cost a long time, because we try many situations, it doesn't work. It doesn't work. I will show you how it. This is very interesting, a very fascinating problem. Is to treat this, and also, for example, so this another very interesting situation is that this y, if y is to this is very symmetric with this one. It's very symmetric in the sense that if I define here utx, uty equals to e phi y plus ty. Okay, where is this? Then I know that this satisfies u ty equals to small g d y u, with u 0 y equal phi y. It's first order PDE, but it's still fully nonlinear because I still have a small g like this. I still have small g like this, which is here is mu upper bound y, here is mu lower bound y. Mu lower bound. And then how to, can we, even the question reached even the case, how we can prove the law of large number by probabilistic method. Okay, by probabilistic. So this one, but so you see so I think, okay, this is the Stan method for law of large number. The Stan, the problem is that how we can understand this P, this I written like this P. P is like this, okay? P is a sublinear expectation. It's like this. So you see, I need to understand this way, this to be in this way. So so V is the solution. Is maybe it's better written like a V. It's written like a V, and we use V is PA is like this. So I define this like P, and then I for any if the theta, if theta is the uncertainty of distributions, if theta, assume that theta is the uncertainty of distributions, and theta phi is what? If phi is given, okay, if I calculate this, and then if I can find a mu which is attain the maximum, if this mu can be attain this maximum, then I write the theta phi, which is the subset of distributions which attain maximum. Okay, this is the important notion in this. Just because we have many subsets. Okay, we have many subsets. If in this way, also we can define phi Sx to be like 1 over S, 1 minus S, and the other one. And then we can prove this lemma. The lemma telling us that if I calculate this and this, it can be defined like E mu S, where mu is the one which attain here. Remember that I have this phi Sx, so phi Sx can be used to be a test function, and using this test function is this is you see this is the class the Wurmberg OU, the OU part, okay, and this, if the classical situation of the Stan method is this is the second order, okay. This is the second order, and which is not which is linear, which is not sublinear. But here I have a sublinear function inside its first order. First order just because it's law of large number. If it's central limit theory, this is just the second order. Okay, it's the second order. So what I mean is the first order is already not trivial. It's still not trivial. And so we can have this. We can define. We can have this and define. Sorry, there's one. I have one. This is the result of this. If I define this is V. If I define this as Vs, Vs is I didn't write there. It is Vs is Ws is E theta S V phi S phi S this as defined here. Okay. So that I can define. I can say that I can prove that. Firstly, this becomes just one S, which depends on one S is important. It's because in this case we can like to treat ODE. Okay, we can treat this like an ODE, and we can prove that in fact it's the positive the upper derivative of W and equals the lower W. This is just because they are Lipschitz. Okay, W is Lipschitz, and then we can prove that like this, and then we can prove that in fact this is the super, this is the lower, so it's the same. Okay, because this equal to this almost surely. Okay, so it's super, it's log. So in this case, it becomes I can prove this one. And then according to this, after this, we can prove that this is proved by Song that the convergence rate is C and minus 1 over 2 is almost not classical, but it is the best one till now. It's the best one to have this minus 1 over 2 as the result. And so the idea of the idea we use is that if we define n phi is like this. So this is a mu for if I have the distribution of uncertainty of theta, I define n phi to be the super of the theta, then this I define like this. Then this n phi is maximally distributed because I explained this maximally. If and only if for any phi in C1b, it's bounded and continuous differentiable, then I have this. This is the formula, the so-called this is the so-called the formula, the Stan formula for law of large number. I have no time to present the case for the central limit theory. Central is you have this like a second order. You just have second order and this is if and only. But for the case where what is important is just for the case where we have mu is in this, okay? The mu is in this is a little complicated. My time is run out. Thank you.